All right, now for the last problem. We look at it, and there's a diver who jumps off of a platform into the water. And so you dive forward and out, so you have both horizontal and vertical motion, so your body is starting to rotate. In figure 2, it shows the person is tucked in, they're rotating faster, and then down at the bottom, they straighten back out to try and enter the water just directly straight up and down. If you've ever seen Olympic diving, you see some people are just amazing at that, going straight up and down as they go in the water. Some people keep rotating over because it's very hard to control. So if we look at that, we know there has to be something to do with rotation, but it also asks a question about energy, and I'm going to talk a little bit about angular momentum. And that's the same idea as when I was spinning around on that chair, and I had the books and would go back and forth to kind of change what was happening. But it says, in this case, why is the person rotating faster in figure 2 than they are in figure 1 and figure 3? So the idea is, so for 2a, here's my written response. The diver leaves the platform. Their mass distributed as far from their center of mass as possible. The diver tucks. The mass distribution and the moment of inertia both decrease. Angular momentum is conserved, so when the moment of inertia decreases, the angular speed must increase. So that's the idea. If you have moment of inertia at the beginning, which is big, you'll have a smaller angular rotation. If then you move so that this decreases, if these two things are still equal, then this must increase. So that's the idea. If you decrease one, you increase the other. There's always that trade-off. And then for part B, I chose the idea that the rotation in number 2, the kinetic energy, is greater than the rotation in 1. And there are two reasons for that. One of them that I didn't state is that you're at a slightly lower point, so more potential energy is turned into kinetic energy. It's not very much, so it's not going to change things quite as much. But the idea is that rotational kinetic energy is 1/2 I omega squared. So it's linear, like if you double the moment of inertia, you have the angular speed. But so what happens in case 2, you've increased the angular speed, but because it's squared, it's going to have a much greater effect. So in part 2, it's not just the fact that it's rotating faster, it's the fact that yes, the moment of inertia goes down, but the angular speed increases the same amount, so if you're squaring that, it has a bigger effect. So you have to go back to the fact that the energy goes like the speed squared instead of just going like the speed itself.